So hello everyone, this is lecture 58 for the mathematical physics. In the last lecture we have seen some product rules and we have seen some second order derivatives, okay, of divergence, gradient and all. So today we will start with line integral, surface integral and volume integral. So I will define you what are they, okay. So consider some vector field A. So you know what is vector field, I already defined you. Now what is a line integral in a vector field? So it is defined as, means you will take the projection of A on every dl1, means see, in this vector space, if this curve is defined A to B, then this A to B curve can be broken into infinite number of dl1, dl2, dl3. Then that projection of that vector field on that each and every dl1, dl2, dl3 and then adding all of them will give you what? Will give you line integral. So A dot dl1 plus A dot dl2 plus A dot dl3 will give you line integral and complete this A to B. And this can be written in this form because this is a very large number, so it will be continuous. That's why we will use the integral A to B A to A dot dl. So this integration represents the summation, so that's why we did this. So this represents this length, complete length will be represented by this. Now see, if this is closed path, means it is not A to B, it will coming out somewhere and it is making closed path. Then we define this integral as in this form, A dot dl, and this not need to be 0, because here it is depending on the path. I mean, we will see that when it is depending on path and not. So but in general it is not 0, okay. Now see, there are two kind of field we have, that is conservative field and non-conservative field. So we call any field conservative only when, if you take the curl of that field that came out to be 0, then you call that field as conservative. And now see, if this field is came out to be 0 and conservative, then this integral will not depend on the path taken by, okay, which path you gone from A to B, it won't depend on that. It will be directly B minus A, means you can directly solve this and it will give you the same value. And see, now it is not depending on path and you are coming back to the A in closed integral, so this will be equal to 0. And A dot dl is independent of path. You can directly calculate the integral and put the limits B minus A will give you the same value, okay. So that is the reason for conservative field. Now see, how we define, means what is the physical significance of this line integral. So we see that when we find the work done, so we do this vector field of force F dot dl, so this represents the work done. So that's how we use the line integral in the real world, okay. Now let's see the surface integral. So consider some vector field A, and if this is your surface in the space and this is your vector field A, then how will you find the surface integral? It will be projection of A on dA1, dA2, dA3. So it will be A dot dA1 plus A dot dA2, and that's all. So summation will give you what? Will give you a surface integral. So I can be represented as summation A dot dA, and it is surface integral, so it can be represented in this form, two integrals, that is surface. So A dot dA, and this is for the open surface. When you have closed surface, you will represent this by this closed contour. So A dot dA, this will represent your surface integral. Now I am just defining these terms. In the next lecture we will see how to calculate these, okay. So how you see your surface integral in the real world? So you know about the electric field flux and the magnetic flux. So there we calculate this surface integral, okay. E dot dA will give you your electric flux, B dot dA will give you your magnetic flux. So that's how you use surface integral in the physics or the real world, okay. Now let's see for the volume integral. Let us consider some scalar function f and particular volume is specified, okay. Then volume integral will be given by this. F is that function and d tau is your volume element and v. So I already told you what are volume element and surface element and the aerial element or the line element. So we already know them. So volume integral can be calculated by this f d tau, and you can, this integral is made up of three integrals. Now see, we can take an example, the real life example. If this function represents the density, charge per unit volume, then this what this volume integral represent, then we will take rho d tau, and this is nothing but charge per unit volume, and this is the small volume. So if you integrate in a particular volume, so this volume element or the volume integral will give you charge in that region, okay. So that's how we can see the physical significance of volume integral. Now theoretically we can find volume integral of this of a vector also, means there it is scalar, but we can find of a vector also. There is no practical definition or the example we have, but theoretically we can define I is equal to a d tau, this A is vector, so it will be ax, ay, az So ax a d tau x cap plus ay d tau y cap, az d tau z cap. And it can be solved in the Cartesian coordinates only. So if you know a in any coordinate system, you can convert them to the Cartesian, then you can solve. So I will tell you that how to solve this, okay. But now just remember this definition, okay. So let's see a theorem which is based on the gradient, fundamental theorem of gradient. So see, if you want to find the line integral a to b del v dot dl, so this will always be independent of the path. So how? See, this is some vector, let's say this is some vector a, and a dot dl is independent of path. Then how can we verify this? A should be, means curl of a should be 0, only then you can say that this is independent of path. So see, if you find the curl of this del v, so you know curl of a gradient is 0. So curl of this gradient will give you 0. That's why you can write this as your independent of path, okay. So it is something like, means you will take the integral and differentiation, the integral will give you v again. So this will be equal to vb minus va. So this will be simply equal to vb minus va. So how we can find this? Means we know that this is our conservative vector and this is independent of path. That's why we can write vb minus va directly, okay. So this is very important result we get to solve the line integral. Now see, if this is a closed path and you have this gradient v dl, that this will be equal to 0 because vb minus vb will be 0. Now to prove this theorem or the fundamental theorem, we'll take an example. Let's say we have a vector field, scalar vector field as x square plus 4xy plus 2yz cube. So we need to find this integral from a 0 0, means path, or the path described as here a to b is this way. It is going from 0 0 0 to 1 1 1, okay. So there are 3 ways we have taken. First we will go from here to here, then here to here, and here to here. Then we will take the second path, here to here, here to here, here to here. So we will go means we are going from here to here in 2 different ways. And third, we are going here to here directly from a to b. So direct straight line from a to b. So we will calculate this integral in all the 3 ways. Then we will see that if they are coming the same or not, and they are equal to this thing or not. So we will prove this theorem. So first vb minus va will calculate directly from here. So v is this, so at this point 1 1 1, it will be 1 plus 4 plus 2, so it will be 6 and 7, and at 0 0 0 it will be 0, so 7 minus 0. So this integral should be equal to 7 from here. Now let's calculate with the first way, means we are going from 0 0 to 1 0 0, then 1 1 0, then 1 1 1. So this is our final destination, but it is first way, second and third. So we'll calculate these 3 integrals. So for the first one, this x is changing from 0 to 1, y is 0, z is 0. So we'll say that dy equal to 0, dz equal to 0, and x is 0 to 1. So we'll calculate first what? Means here we need this gradient of v. So gradient of v, and v is this. So gradient of v will give you, means first with the x, you need to calculate the differentiation with respect to x. So it will be 2x plus 4x, and that will give you I cap, x cap, 2x plus 4y. Then with respect to z, sorry y, it will give you 4x plus 2z cube, y cap. Then with respect to z, so it will give you what? 3 to 6, 6yz square. So this is your gradient of v. Now you need to product a dot product with the dl. So dl is what here? Dx I cap, and other terms are 0 0. So you will have only dl as dx x cap. Now gradient multiply dl, what it will give you? It will give you, this will cancel out, so it will be 2x plus 4y dx. Now see, in this path y equal to 0, so it will give you 2x dx. Here it will be x square by 2, so it will be x square only, and integrating will give you 1 here after putting the limit. So this first term is giving you 1. Now let's calculate for the second one. Here x is constant, that equal to 1, and y is changing 0 to 1, and z equal to 0. So dx equal to 0 because this is fixed, dz equal to 0, but dy is not equal to 0. So dl will be dy y cap here, and gradient we already calculated, and dl, so only this term will be exist, others will be eliminated. So it will give you 4x plus 2z cube dy from here. because it is dy multiplying with this will give you this term. Now see this z equal to 0 and x equal to 1, so it will give you 4 dy. Now integrating this will give you 4y and solving this will give you 4. Now this is for the second path. Let's take for the third path. Now we are here, so x equal to 1, y equal to 1 and z is changing 0 to 1. Now this dx will be 0, dy will be 0 and we will get dl as dz z cap. So gradient v dl again will give you this z term again. From here you will get 6y z square dz. Now this y equal to 1, substitute here, so it will be 6z square dz. It will give you what? Z cube by 3 will give you 2z cube and it will give you 1, means 1 minus 0 and multiply 2 will give you 2. So solving this it will give you 2. Now this complete integral will be sum of all these three parts. So it will be 1, 4 and 2. So it will give you 7 again. So that is the same result we were getting directly here. So this is proof that you can take this by any way, you will get the same result. But let's check for the second path also, if you are getting the same or not. So this is your second path. First we are going from 0 0 to 0 0 1, then up to 0 1 1, then 1 1 1. Okay, so let's calculate for the first path. X equal to 0, y equal to 0 and z is going from 0 to 1. So dl will be dz z cap, and we know already the gradient. With dl it will give you 6y z square dz. Now y equal to 0, so this will give you 0. For the second path it will be, means x equal to 0, y is going from 0 to 1 and z equal to 1. So dy equal to dy y cap, dz equal to 0, dx equal to 0. So gradient v dl will give you dy, and here you have x equal to 0 and z equal to 1, so it will give you 2 dy, and after solving this will give you 2. Now for the third path, x is going from 0 to 1, y equal to 1, z equal to 1. So dy equal to 0, dz equal to 0, dl equal to dx x cap. Now gradient v dl will give you 2x plus 4y dx. In place of x, it will remain as it is, y equal to 1, so it will be this. Integrating this and putting the limit 0 to 1 will give you 5. Now this complete integral will be sum of all these three paths, so 0 plus 2 plus 5 will give you 7 again. So you are getting the same result, means this second path also. Now let's see for the third path also, means directly a to b. Now see this line 0 0 0 to 1 1 1, you see that x equal to y equal to z all through the path, just like in the 2D you have, if any line passing means at a 45 degree, then x equal to y is the equation of the line passing through the center. Same here, it is x equal to y equal to z, because it is 1 1 1 here. And see, all are going from 0 to 1 directly. So dx equal to dy equal to dz, and del v dot dl will give you 2x plus 4y dx, dy and dz. Now see, we have these two equations, so x equal to y equal to z, so we'll take in any one variable. So y equal to x, z equal to x, and here also y equal to x, z equal to x. And in place of dy we have dx, and in place of dz we have dx. So we'll solve in the only one variable, because we know this condition. So we'll get this thing after integrating. Then it will be 5x square. So there is this correction. We get this equation after integrating itself. So it will be 6x, it will give you x square by 2, so it will be 3x square. Here it will be 4x, so it will be x square by 2, so it will give you 2x square. Same here, it will be x4 by 4, so it will give you x4 by 2. And here it will be x4 by 4, it will give you 3 by 2 x4. Now it is 5x square, and it will be 4 by 2, so it will be 2x4. Now just put the limit 0 to 1, so it will give you 7. So we are getting the same result with any path. So that's how we proved this theorem, and it is very useful, means you can take any path, and if this condition is satisfied, then you can directly calculate your line integral. Okay, so this is a very important result we get, and we will use in the electromagnetic theory. So let's end today's lecture here. In the next lecture we will see the surface integral and the volume integral, how to calculate them. Okay, so and the other theorems also. So thank you everyone.